And we've got a nice big waves question to finish today, so have a go at this one. Okay, so we have an open pipe and a stationary wave in it, and we're asked to explain how and under what conditions the stationary wave is formed. So we're going to say, the sound wave travels down the pipe. It is reflected at the far end for the first mark. The reflected wave superposes with the original wave, adding up to give nodes and antinodes for the second mark. And for the third mark, that's the conditions. Now, it's a sound wave, so it's longitudinal, but we're going to represent it as a transverse wave because it's much easier to see where the nodes and antinodes are there. Because it's an open pipe, we need antinodes at both ends. That's the condition. And this means that this will happen if the length of the pipe is equal to a whole number of half wavelengths, a whole number of half wavelengths. So here's one half wavelength, here's two half wavelengths, and so on. All right, the next part asks us to describe the motion of the air particles at Q and at P. Well, at Q, we've said that we've got an antinode. And so that means we know it's oscillating with maximum amplitude. Those air molecules are going to go maximum distance away from their equilibrium position in both directions. But we've also said it's a longitudinal wave, so they're oscillating that way. So here you get 1 mark for saying maximum amplitude and 1 for saying from left to right or along the pipe. But P is 1/4 of a wavelength back from Q. Well, if we're here and we go 1/4 of the wavelength back, we end up there. So P is a node. And so for 1 mark, the air molecules at P don't move at all.